All right, it looks like we have a great group here. So without further ado, Glenn, take it away.
Thank you, Michael. Appreciate it. Hello to everybody. It's Glenn McGilvery, Managing Director of the Institute for Catastrophic Loss Reduction. Welcome. Today, while we are having a typical Friday Forum, it's also atypical. It's also a time where we are launching a major paper. This is the fire following earthquake in the mainland of British Columbia effort. This was just posted on our website about an hour ago. Press release went out an hour ago. It's a big day for us. This is a major paper. Charles Scawthorn, a leading international expert on the issue of fire following an earthquake, will go through his results. Charles did a similar effort for us last year, fire following earthquake in the Montreal region, and did Vancouver 19 years ago for ICLR. This is an update of that paper. The numbers, I think, are a little bit more disconcerting this time around. So with that, I'm going to hand it over to Charles, and Charles, take it away.
Thank you so much, Glenn, and hello to everyone. It's my pleasure today to speak to you on this topic. My co-principal investigator is Professor Keith Porter, who's on the line also, but in the interest of time, I'll be giving the entire presentation. As Glenn said, topic is fire following earthquake in the Lower Mainland of British Columbia. This is the outline of what I'll be speaking to. Do brief introductions and then go through the choice of earthquake scenarios, the analysis, results, and we're going to spend a little more time on the opportunities for mitigation, how to reduce this problem. And then we'll have a conclusion discussion. There's a lot of people who helped us with this study, and we want to acknowledge them right now. The City of Vancouver, fire, emergency planning, other cities and jurisdictions in Lower Mainland, Natural Resources of Canada, and of course, people at ICLR. Thank you very much. Glenn briefly didn't really do justice to ICLR. It is a world-class center. I think most of you may be familiar with it. It serves the insurance industry, not-for-profit, affiliated with Western University, and has a board of directors of rather eminent people. With regard to SPA risk, we are an independent consultancy. We focus on natural hazards risk management. There's two of us, Keith Porter and myself, and we'd like to tell you a lot about ourselves over the next hour or so, but in the interest of time, we'll simply say that I'm a structural engineer and retired professor of infrastructure risk management. Keith is also a structural engineer and a research professor at the University of Colorado at Boulder. So enough about us. As Glenn mentioned, almost 20 years ago, we did a study of fire following earthquake risk in the Lower Mainland. I think that has been used by the industry, but it's Vancouver's changed quite a bit, as well as us having more data and so on. So ICLR asked us to do a new analysis. Call it an update. It's really a new analysis based on a lot of new data, both for Vancouver and on the issues of fire following earthquake. We have 20 more years of experience. So that's what I'll be speaking to today. Many of you are familiar with the Lower Mainland. It's not just the city of Vancouver. It's a total population of 2.5 million people, consisting of many jurisdictions, as you see here. And this is the road network, which gives you an idea of the population density, distribution of population within the Lower Mainland. Much of it is located on the Fraser River Delta, meaning it's a soft alluvial deposits, which result in strong shaking in an earthquake. This is a photograph of the aerial photograph of the Lower Mainland. It is one of the largest concentrations of high-rise buildings in North America, in the city of Vancouver. And of course, there are high-rises in other parts beyond the city of Vancouver itself. Cities such as this are threatened by major fires at all times. The fire on the lower right is San Francisco a couple of years ago, and the fire on the left, of course, is Grenville Tower in London. Now, I'm not suggesting that the conditions at the Grenville Tower in London exist in Vancouver, but simply include this because it's well known and an example of a high-rise fire, in that case, exacerbated by poor construction techniques. But people are familiar that cities are threatened by these kinds of fires at all times. What they may not have as much at the forefront of their consciousness is the fact that we are also threatened in locations like Vancouver by fire following earthquake, which this photograph shows affected San Francisco in 1906. However, that was over 100 years ago, and it's not just a historical thing about fire following earthquake. This was 1989 in San Francisco, and this is Tokyo in 2011. So fires after earthquakes are a real hazard that are with us today when earthquakes occur, and the fires are quite likely to spread in urban regions with a lot of dense wooden construction, such as we have in Western North America and in Vancouver. Now, I'd like to describe the process of how fires, why they're so serious after an earthquake and how they develop. This diagram shows, I'm going to use it to illustrate the process. The x-axis is time, and the y-axis begins at time 0 at the time of the earthquake. And each of those numbered boxes, the red boxes, represent an ignition. Many of those occur soon after the earthquake, during the earthquake, or soon afterwards, and some of them are delayed. They may have causes such as electrical or chemical reactions and so on. Those fires start to grow, and I'm talking here only about fires that require a fire department response. Other small fires that people can put out are not included in this. So these require a fire department response. And the fires are growing, and the size of the fire, the growth of the fire, is indicated by the width of the bar. Each bar represents a fire that requires one fire engine to suppress the fire, to control and suppress it. So they all start out with one bar, but some of them quickly grow to 2 and 3 and 4 bars and so on. Now, under normal conditions, the ignitions would be discovered relatively quickly. But after an earthquake, there is often a period of delayed response, a delayed discovery, and discovery is indicated by the letter D. And that's because people leave the building and they're out in the street and so on for a while. When they come back in, they realize there's a room on fire, and then they go to try to report it. And the report is delayed because when normally these days, fires will be reported by telephone, and the phone system, while it may sustain some damage, is fairly reliable from the point of view of the hardware, but it will be saturated. It will be difficult to get a dial tone. So there will be a delayed response. Meanwhile, the fires are continuing to grow. Eventually, the fire department goes to the fire, either because they receive the response or they just see the column of smoke, and they go to the fire. And for example, in ignition number 8 at the bottom there, they will suppress that fire, and we change the color of the bar from red to blue, meaning the fire is suppressed. And that engine, once it's controlled and suppressed the fire, moves on to another fire. And for all the other ignitions, the same process is happening, and they all start to converge. To the extent that they can control the fires, they then start to converge on fires that they cannot control. And the question is, do those fires turn into a major urban conflagration? It's a race against time. That's all it is. So that's the process. Now, to analyze that process, we go through a standard logical flowchart type of analysis, taking into account many factors. I'm not going to go into detail with this. It's simply, we define the earthquake, what nature does. We define the assets at risk that we put in the way of what nature will do. We then take into account the fire department response, the response of various infrastructure such as water systems and transportation and communications, and track the fire spread. And I'm going to walk you through each of these major elements and to show you how the analysis was done. First, by defining the earthquakes. Well, the Lower Mainland is really dominated by the subduction zone that is offshore and passes underneath the Lower Mainland. It's the so-called Cascadia subduction zone. It's capable of a magnitude 9 earthquake, just as occurred in Japan in Tohoku in 2011, and in the Indian Ocean in 2004. And last occurred here in the year 1700. So whatever, 320 years ago. Now that earthquake may not yet occur for decades. It could occur in moments, but it may not yet occur for many decades. But you'll notice that beyond that, there are also other seismicity associated with this subduction zone, which is part of the entire process. There are the deep earthquakes, such as occurred in 1949 and in 2001, and there are shallow crustal earthquakes that occur near the surface. Now, the timing of when this might occur, there's been a lot of work done on that, and the best estimate is that there's a very significant probability in the next few decades, on the order of 1 in 5 or so on, that we'll have that magnitude 9 earthquake. However, we need to understand, again, the timing of these events. This shows the two plates that are locked. On the left is the Juan de Fuca plate, which is subducting beneath the North American plate, and they are locked. So as the Juan de Fuca plate on the left passes beneath the North American plate, it pulls it down, and the plate is deformed, as you can see, in various locations. Eventually, that locked section will slip, and that is the magnitude 9 earthquake that will occur. Now, I've numbered that third because in the sequence of events, that is the third event to occur. Prior to that, we will have magnitude 8 events on the slab, at the interface, or within the slab, relatively deep, but still magnitude 8, and they can cause very strong shaking at the surface. And also that North American plate is being bent and deformed. So we have shallow crustal events, which are occurring even prior to the magnitude 8s and concurrently. And these are very close, indeed, if not directly underneath the Lower Mainland. And actually, they result in the strongest shaking, rather than the magnitude 9 Cascadia event, which is rather far away. So these are the primary threat, really, to the from a shaking point of view. Not tsunami, that's the magnitude 9, but from a shaking point of view, these are the fire afterwards. These are the primary threat. The Natural Resources of Canada, Geologic Survey of Canada, has done a lot of studies and disaggregated that, which confirms what I was just saying. And based on that deaggregation, we have chosen 5 scenario earthquakes to examine in this study. These are the same scenario events that are being used by Natural Resources of Canada to look at shaking damage, and we use them for fire so that the decision makers will have the same events on an apples and apples basis. The 5 events starting in the west or at the left are the magnitude 9 Cascadia subduction zone. Of course, we have to look at that. It's over 300 kilometers from Vancouver City Hall. And then the lower southernmost event is the Leech River Devil's Mountain event, of magnitude 7, on Vancouver Island or close to Vancouver Island, but still over 100 kilometers away from the city of Vancouver. And then 3 events that are actually shallow crustal events very close to the city of Vancouver. We term these the Georgia Strait event, which is a magnitude 7.3, the Juan de Fuca event, which is a magnitude 6.8, and we've put a shallow crustal magnitude 6.5 directly underneath the city of New Westminster. Nothing against the city, but we just located it there as central to Lower Mainland. This table shows the 5 events, and I'll be presenting results for those 5 events. So having defined these events, we can attenuate the ground motion and estimate the shaking within the Lower Mainland due to each of these events. Of course, shaking is affected by the different kinds of soils, and so we used data from Natural Resources of Canada. The specific data we use is something called shear wave velocity, or VS30, which is the average shear wave velocity in the upper 30 meters of the soil column. And what's important to note here simply is that the hotter the color, the poorer the soils, and the entire, as you can see, much of the Fraser River Delta is very soft soils, which is, anyone who knows the Vancouver area knows this very well. So we'll have very strong shaking with the hotter the color. Given that, we can attenuate the ground motions and estimate the shaking. And this is for the magnitude 7.3 Georgia Strait event. We are showing the median shaking in this diagram. As you can see, within the Lower Mainland, the median shaking varies from on the order of about 0.2 G to as much as perhaps 0.5 G. Now, 0.3 or 0.4 G is very strong shaking. This is a fraction of gravity, the force of gravity. So if you weigh 150 pounds and are subjected to 0.3 G, it's like being hit in the midriff with a 50-pound sandbag, and that'll affect most of us. May not knock us off our feet. It could, but it'll certainly set us back. But that's just the median shaking. We need to understand that actually the shaking here and there is much stronger than the median values. And let me illustrate that. There's the median shaking diagram again. But let me illustrate this by talking about median heights of people. If we take the population of adults, we can average out and get a median value. But all people are not that median value. We all know this. Some are shorter and some are taller. And this is the reality. And if we were, for example, designing a doorway, we cannot use the median value to design the doorway. We have to take the median plus some delta for the height of the doorway. Otherwise, we're going to have a lot of lumps on heads and so on. In the same way, the ground motions need to have into account this variation. And we did this in our Monte Carlo simulations by using 100 realizations of the ground motions. We used more than 100 realizations of Monte Carlo, but we used 100 realizations of ground motion, which were used in our analysis. And here are just 3 of those realizations calculated taking into account spatial correlation. And you'll see that as opposed to the median values, here and there we have you may want to call them measles, of much higher ground motions on the order of 1 G. So if you weigh 150 pounds, you're in one of those red spots, you're being hit in the midriff with a 150-pound sandbag. And that's going to knock most people off their feet. And it's going to severely stress most buildings and collapse a number of them. Now, this is the reality of what the actual shaking looks like. If you notice, next to each of the red spots, there is a paler green or yellow spot. And if you average those, that's how you get back to the median value. But the median value is not the representation of reality. It's these measle diagrams are actually what the shaking looks like. And in each one of those areas where we have the stronger ground motion, we will have many more pipe breaks and ignitions. And those, because the water system is interconnected, the breaks where the ground motions are high affect the entire system, as I'll discuss. So we took this into account. We also took into account permanent ground displacements or liquefaction. This is a photograph from the 1994 Northridge earthquake, where we had ground failure. It broke water mains and gas mains. You can see the fire resulting from the gas main there. There are a number of houses were lost through the fire at this location. And in order to map this for the Lower Mainland, we have a mapping from Natural Resources of Canada of the areas of liquefaction susceptibility, and the softer soils are more likely to liquefy. You'll notice that much of the Lower Mainland has at least a moderate and if not a high and very high potential for liquefaction. So, and liquefaction, of course, means the water pipe network in that area will be severely compromised. So that's what nature does. What do we put in the way of nature? Well, we put on all these buildings and other infrastructure. I won't spend a lot of time. The report details all the data we collected on that. This is simply a mapping of the building density in terms of square feet per grid cell. And you can see that there's hundreds of thousands, or actually millions to tens of millions of square feet per grid cell in the exposure here. And the analysis was actually not just done at the grid cell, it was done on an individual building basis. We have data on every building in the Lower Mainland, building footprints, heights, ages, and so on and so forth. And this allows us to model the fire spread. Again, I won't spend a lot of time. Simply, we have a lot of data here, and it was all used in the analysis, and it's in the report. There are some things that are unique about the urbanized area of the Lower Mainland. One of those is the overhead electric distribution lines. It's rather unusual in North America. As a matter of fact, Vancouver is the only city I really know about in North America that has overhead electric distribution lines in the central business district. And we had pointed this out in the study 20 years ago. And since then, the electric utility has been undergrounding the distribution lines, but it's a gradual process, and there's still a significant amount of overhead lines in the central business district. And each of these, of course, with their transformers, is a source of ignition close to buildings. So that's a particular situation in the city of Vancouver, or at least the central business district of the city of Vancouver, that exacerbates this problem and is different from many other cities in North America. So having defined what nature does and what we put in the way of nature, we then have to estimate the ignitions. And the estimation of ignitions is based on empirical relationships developed by myself and others. This is a diagram that simply shows the frequency of ignitions as a function of shaking intensity. These ignitions are due to a number of different sources. About a half of them are typically due to electrical ignitions, and this data is from a study I did of the Northridge earthquake, funded by the National Science Foundation. About a third are due to gas-related appliances and gas line breaks, and a quarter or so are due to other sources, such as friction, industrial processes, exothermic chemical reactions from spilled chemicals, and so on. So with that, we can estimate the likelihood of ignition throughout the area, and this is one of many diagrams for each of the scenarios that we generated showing the distribution of ignitions. Given these ignitions, as I mentioned before, they will be reported hopefully to the through 911 in Vancouver. They have a very modern 911 emergency reporting system, communication system called ECOM. I have reviewed this building and somewhat familiar with its operations. So the reports, in many cases, will get through to ECOM. As I said, not always, but again, the reports will be delayed. The 911 centers will be overwhelmed. They have only a few dispatch operators on duty typically, and they don't know when the earthquake's coming. They do have standard operating procedures to quickly put other additional operators online. Managers will actually put headsets on and get to work, but still they won't have enough until they get recall of off-duty personnel. So the 911 centers will not be able to handle the calls, and some will not go on. So, and fire departments do not have their own helicopters in the Lower Mainland. Actually, relatively few fire departments in North America have their own helicopters, so it's not a criticism of the fire departments. So TV and helicopter news reporting will be a valuable resource for a few of the incidents, but the TV helicopters are not the same trained observers as fire departments, so they're not going to miss a lot of the fires. And quickly gaining an accurate and complete situational awareness will be a challenge. And fire department dedicated UAVs, unmanned aerial vehicles, or drones, unpiloted aerial vehicles, would help the situation. A lot of the fire departments in North America are now moving to put drones into their standard operations. Vancouver hasn't really, is in the process of prototyping this. So that will be an improvement going forward. Not at the moment, but in the near future. Next is, once they have the report, they need to get to work. There's 99 fire halls in the Lower Mainland. This shows their distribution. Each of the green icons is one of the 99 fire halls. And as you see there, each of them exists within a cell. We did not have data on the actual first response area, which is simply an artifact anyway. So these diagrams are so-called Voronoi diagrams, which represent equal distance between each of the fire stations. And we assume that the fire engines will initially respond to ignitions within their own cell, if there is an ignition. If not, then they will go to aid fire engines at in the next and neighboring cells, and so on. And we track their movement in the computer codes we use to do this analysis. We take into account the resources of all the fire departments. This is some of the resources of the city of Vancouver, which is the leader in the area. They have the most specialized equipment, the most equipment and the most specialized equipment. The upper left is their typical fire engine, Class A fire engine. They have several fireboats, as you see there. And the lower right is a so-called hydro sub. It's a specialized piece of pumping equipment with large diameter. The yellow is large diameter hose that they use. And on the lower left is a so-called hose tender, which carries a mile of that large diameter hose. And the hose tender and the hydro sub and the yellow hose allows the fire department to lay an above ground water main system in the event that the normal water main system fails. So the city of Vancouver has several of these hose tenders and has a reasonable capacity to deal with broken water mains. However, to improve that, the city has recently acquired these hose reels, and each of these reels, they have 3 of them now, carry a mile, actually 6,000 feet of the large diameter hose. And they can quickly, these are towable, they can quickly be towed down the street, laying that hose and creating additional above ground water main systems and moving water. So the City of Vancouver Fire Department, actually Vancouver Fire and Rescue Service, has been very proactive in about earthquakes, and as you can see, has a lot of good equipment here, and its capacity, I think it's fair to say, far exceeds really any of the other neighboring jurisdictions. The reason they have this is that the water main system will likely be compromised after an earthquake. The water system consists, first of all, of the Metro Vancouver transmission line system. The Lower Mainland gets much of its water from several reservoirs on the North Shore, and those reservoirs transmit, or the water is transmitted through under submarine crossings of Burrard Inlet at several locations, and they have within the Lower Mainland a number of terminal reservoirs, and Metro Vancouver over the last 20 plus years has been moving to seismically upgrade this system. Actually, I consulted to them a few decades ago about this, and I think they've done a great job. A matter of fact, broadly speaking, the Lower Mainland has been one of the most proactive communities in the world, I think, in mitigating earthquake risk. But there's always more to do, and that's what we're talking about today. So Metro Van has done a lot to improve and get the water to the terminal reservoirs. However, it's the last mile that's most important, getting the water from those terminal reservoirs to the hydrants. And for that, we must rely on the potable water distribution network. We have the data on that entire network, as is shown here. We know the sizes of the pipe, the age of the pipe, the material that the pipe is constructed of, and other details, which allow us to estimate the vulnerability of that pipe. And it is vulnerable. There will be breaks. We know this. So in terms, and the fire departments know this. And fire departments or fire officers are resourceful and will adapt to the breaks. To do that, they will access so-called alternative water supply. And that would mean drafting from a swimming pool or a river, a lake, whatever, to get water if the hydrants are dry. So we mapped the alternative water supply and quantified that in terms of what we call an alternative water supply factor. Blue is good, red is bad. And as you can see, most of the Lower Mainland is the alternative water supply factor is quite low, meaning likelihood of being able to have water at a fire ground is quite low. Why is that? Because while the water is there in the Fraser River, the fire departments do not have the ability to move it from the river to the fire ground. Moving large quantities of water a mile or so is a very difficult task. This is why the City of Vancouver is acquiring additional equipment, and most fire departments cannot do that. So we took that into account. We also took into account, of course, the City of Vancouver's dedicated fire protection system, which is a unique, almost unique, high-pressure system dedicated for protecting the central business district and high-density areas like the Kitsilano from fire. I was a consultant. I was the earthquake consultant on the construction of this system 25 years ago. It is modeled after San Francisco's high-pressure system. And is I can't praise the City of Vancouver highly enough for building this system and maintaining it and extending it. So we took this into account, and it does protect these areas. And that's why on all the maps and so on, you'll see that the areas where they have a DFPS are generally have a lower risk, with one exception I'll come to at the end. So given that, for every one of the Monte Carlo simulations we ran, we took into account the shaking and the permanent ground displacements and generated a overall water supply factor, meaning what is the likelihood of having water at the fire ground, taking into account the damage to the water system, the alternative water supplies, everything. And this is just one of hundreds of realizations. And it shows, again, blue is good, red is bad. So where there's red, they're unlikely to have water. And without water, the fire departments are pretty helpless. And they will, the fires will, they'll have difficulty in putting the fires out without water, and the fires are very likely to grow. So that's the situation there. So taking all of that into account, we can then estimate the losses due to fire. This is for the magnitude 9 Cascadia subduction zone event. Again, it's over 300 kilometers away. The shaking is shown in the upper left. It's quite low, actually. And on the right then is the mean number of ignitions, the distribution of those. Again, the numbers are perhaps you cannot read those, but they're all in the report. And in this event, actually, we ran in Monte Carlo, so we have a distribution on the number of ignitions for every one of the grid cells. But the total number of ignitions for the Lower Mainland is on the order of a dozen or so, 1 or 2 dozen. So it's really not that bad an event for the Lower Mainland. A couple of dozen ignitions is a busy day for the fire department, but given the 99 fire halls and all the equipment that they have there, I think they can probably handle this with, they'll have 1 or 2 conflagrations. There is some loss. As a matter of fact, this is the distribution of the losses we estimate, the median losses, and the median losses will be on the order of $0.16 billion. So in other words, $160 million of mean losses. And that's not an inconsequential amount. That's a lot of money. But for Canadian insurance industry, $160 million loss for fire here is something that they have handled in the past. It's much less than the losses in Fort McMurray, and it's really almost a no never mind, unless of course your house burns down. But from the regional perspective, this is not so bad. However, we can look at the next event, which is we'll look at one more event, the magnitude 7.3 Georgia Strait event, which is a shallow crustal event, very close. Again, the median ground motions, and recall we took into account the uncertainty on that. We have the number of ignitions shown on the right, the distribution of ignitions shown on the right. And here now we're talking about a couple hundred fires. Whole different picture. And this is beyond the tipping point. The fire services will not be able to address all these fires, and as a matter of fact, a number of these fires they won't have water to fight them anyway. So we're talking about dozens of conflagrations, and This shows the overall final distribution of losses, and our estimate is that this could be in the median about $10 billion in losses due to fire for this event. This is only one of the 5 events we looked at. Of course, we also have a distribution on the losses, and that's all in the report. So, and just as you see, there's significant uncertainty or variance on the number of ignitions. There's significant variance on the losses also. So it could be less than 10 billion or significantly more than 10 billion. Here's the summary results for the 5 events, and you can see that 3 of them are numbers that should make you sit up and take notice. $7 to $10 billion, quite a bit of money for these 5 events. For 3 out of the 5 events, the Leash River event in Vancouver Island is negligible, and the Cascadia subduction zone is very modest losses, only 16 ignitions on average. From an insurance perspective, you know, you're in a better position to judge this than myself. You know that this is it's fire, so it's almost entirely insured. There's been a lot of discussion within the Canadian insurance industry about what the total losses due to fire after an earthquake, plus shaking, plus business interruption, and so on and so forth, that this could result in financial contagion. Swiss Re has papers on this, and other authors, that you could have a domino effect within the industry, and that it could extend beyond the insurance industry to include the finance and real estate sectors. And as some of you know very well, this is being addressed by industry and government. It's not part of our report. I just mentioned it because these are significant numbers. Now, what can we do about this? Well, we identified 4 major areas where their interventions are possible, specific to fire following earthquake. We're not talking here about reducing earthquake losses. We're talking here about focus on reducing fire losses. And there are fire service opportunities, water service, building standards, and energy industry. And I'll speak to all of those. But let me just mention to you, prior to today, we have had one-on-one briefings with the fire service, with the water sector, with the building code community, and with the energy sector, in which we went over the same presentation I've just given you and focused on the mitigation specific to them. And the reception has been generally very good. They all take this seriously, and actually in several of these sectors, they're interested in proactively moving ahead on the recommendations that I'm about to present to you. These recommendations, first of all, with regard to fire hall vulnerability. If the building collapses or the doors can't be opened, then it's a non-starter, literally. However, we don't see that as a problem here. I just wanted to mention, I think this has largely been addressed in the Lower Mainland. So the fire stations are relatively modern and structurally sound, and the various jurisdictions have been responsible in this regard. However, we've identified that they should think about earthquake early warning, particularly with regard to being able to get the doors open and the apparatus out before the Cascadia damaging shaking arrives at the Lower Mainland. And actually, Keith Porter, the co-principal investigator on this study, has a complete discussion of this. The URL is shown there, and if you go to the SPA website, you can read about this. And this kind of technology is being used in California, and actually Vancouver Fire and Rescue does have this partially. They have sensors at the fire stations, but what they need to do is put sensors over on Vancouver Island so they get more lead time in their warning. And we discussed this with them, and they're in the process of doing that. We're pleased to see that. The other jurisdictions probably need to take this under advisement. With regard to water supply for firefighting, as I mentioned earlier, Metrovan has been very, there's not much that we could tell them to improve there. They're doing a great job. Vancouver Central Business District, the dedicated fire protection system, kudos to them. Vancouver Fire and Rescue, having emergency water movement capacity, kudos to them. But the other water districts and fire departments are generally, we believe, not so well prepared. So therefore, our recommendation is that they develop a firefighting water capacity. This equipment here is from the San Francisco Bay Area, and it shows a hose tender with a hydro sub, like Vancouver has. Again, in the entire Lower Mainland, 2.5 million people, they only have a couple of these. So what we recommend, cost the Lower Mainland is almost surrounded by water, just as San Francisco was in 1906. That's not enough. What you need is a regional portable water supply system. We recommend it be developed where every jurisdiction has one or more of these kinds of units with a set miles of hose and hose reels, whatever, that all of that equipment be consistent and compatible with fittings so that they all can interconnect, and the procedures, the terminology, their operating procedures all be the same so that they can work and play well together, and that they regularly do that they regularly have interdepartmental exercises and be in a posture following an earthquake to be able to aid each other where the conflagrations occur. They don't have this now, and we made this recommendation, and it was received very positively. And I think that we're going to be working with them moving forward on making this a reality. I mentioned that Vancouver is among the highest concentrations of high-rise buildings in North America, and these buildings are mostly quite modern. There are some older ones, but Vancouver's seen enormous growth in the last few years, and these things have been popping up all over. Structurally, from an earthquake point of view, they should form reasonably well, but the issue of fire still exists. And we know this is the 1991, the fire in 1991 in the First Interstate Bank building in Los Angeles, the tallest high-rise in California at the time. 4 floors burned out, but all the floors below sustained terrific water damage, and all the floors above terrific smoke damage. And it took half the Los Angeles City Fire Department to control this fire. So one high-rise fire is a challenge for any fire department, whether it's Tokyo, New York, Los Angeles, or Vancouver. And after an earthquake, it's quite likely you could have a few of these. This diagram shows a high-rise. It's from a book I had on fire safety and high-rise tall buildings from a number of years ago, and all the fire-related aspects. The thing I want to focus on here is secondary water supply. The California Building Code for the last 50 years has required a automatic secondary on-site water supply for high-rise buildings, defined as a usable capacity for the sprinklers of 30-minute supply to the sprinklers. This will typically calculate out as 15,000 gallons or more. And this means a tank typically in the basement. And why is this? Well, it's recognized in California that the sprinklers are typically supplied from the water mains in the street. In an earthquake, those water mains are going to fail. Not only the hydrant's going to go dry, but then the sprinklers won't have any supply. So you need to have a secondary water supply for high-rise buildings because of the concentration of value and the higher potential for ignition on site in that location. So this has been a requirement in California for the last 50 years. No similar provision exists in the National Building Code of Canada or BC Building Bylaws or the City of Vancouver. I was a little surprised when I discovered this. And this has been confirmed. We've had discussions with Vancouver building officials. They confirmed this. And we identified that they should have a provision like this. And They, again, this positively, as a matter of fact, the Professional Society of Engineers, Scientists of British Engineers and Geoscientists of British Columbia has seized this, and I think this will be moving forward in their code writing process. Bear in mind, this requirement of a secondary water supply is only for high seismicity areas. It's not for all of British Columbia or all of Canada. It would affect, but it would affect the entire Lower Mainland. And what are you talking about here? Well, 15,000 gallons or 60 tons of water is simply a cube about 4 meters on a side. And this is really just one parking place in a basement with 3-meter tall walls. So we're talking about sacrificing one parking place to do this. As a matter of fact, in the basements of high-rise buildings, you have your backup fire pumps and your backup power supply for the fire pumps. And in California, you have a tank like this next to it, which supplies those fire pumps. So all we're talking about is putting in a tank, something like this, in high-rise buildings. Not only new ones, but this really needs to go in all the existing high-rise buildings. It's too bad it was, since many of them have been built in the last decade or so, it's too bad this requirement hasn't been there already. We're not talking about a lot of money. You can go out and buy a 15,000 gallon plastic water tank for $1 a gallon. Of course, installing it, the labor and so on, we might be talking $100,000. And maybe it's not a plastic water tank you put in there, but as you saw in the previous photograph, a steel tank. So it may be $100,000, but to spend $100,000 to protect a high-rise building, which has values of hundreds of millions of dollars, the benefit-cost ratio, I think, is obvious. So that's with regard to the high-rise buildings. And again, that recommendation has been warmly received by the building sector, and we will be working with them to move that forward. The energy industry was not assessed in this study. The energy assets, the LNG terminals, marine oil terminals, oil refineries are vulnerable in earthquakes. They are typically damaged in earthquakes, and particularly by fire, and they exacerbate the fire following earthquake risk. But the analysis of those are a specialized topic. We didn't get into it in this study, but we recommend, and this is an example from the 1999 Turkish earthquake of the oil refinery there on fire. And Keith Porter and I were both there following that event. We recommend that first, all the major energy facilities in the Lower Mainland be reviewed for seismic vulnerability. Now, we didn't delve into this. Some of them already have been. We recognize that. We understand that. And that's good. Responsible owners have done the right thing. But some of the others, either their seismic vulnerability studies are dated or they don't exist at all. And there really ought to be a review of all the major energy facilities, not only from the point of view of fire following earthquake, but also to, frankly, to assure that they continue to function following the earthquake to serve society. With regard to gas, recall that the gas was a major source of ignitions. So we recommend that the gas operator in the area review its ability to control and isolate the gas transmission and distribution network in the event of a major earthquake, and consider a seismic gas shutoff device in the gas meters. And let me explain those two things. The gas network, the underground gas mains, just like the water mains, are going to break. In recognition of this, Tokyo Gas and every other major gas operator in Japan has developed a system of dividing their transmission and distribution network into a series of blocks. This is Tokyo, and you can see here that they've divided it into almost 300 low pressure blocks and a couple dozen medium pressure blocks. And each of these blocks has seismometers within there that measures the ground motion, and if the ground motion exceeds a threshold amount, automated valves will close off and isolate that block to reduce the amount of gas that would be feeding fires. The system has worked very well in a number of earthquakes, and in the analog for the Cascadia subduction zone, that is the 2011 Tohoku earthquake, it worked very well in Tokyo. Within 5 minutes, the system had retrieved all the data. They knew where they had strong shaking within their service area and what blocks had been isolated. And so it worked very well. And I visited Tokyo Gas and discussed this with them and Japan Gas Association. So we recommend that the gas operator in the Lower Mainland look at this and hopefully move ahead on this. The other side of that coin is stopping the gas flow actually into the building. And we strongly recommend that a seismic gas shutoff device be included in all gas meters. Now, let me explain that. When I say a seismic gas shutoff device for gas lines, to date, North America, you're probably thinking of something like this. These are, you can buy these on Amazon. They cost on the order of $100. There's half a dozen different manufacturers, the COSO valve and so on. And these valves, while they cost on the order of $100, they have to be cut into the, you have to cut the gas line and have a licensed plumber install it. And I found one offer online to do it for $430 in California. That's US dollars. But frankly, it's usually more than that. It's usually over $500 to install these in the line. How do they work? A diagram is shown here. I mean, it's a trivial technology. You basically have the pipe come in one side. You have basically a little trap door that is held in place. And if the shaking exceeds a certain amount, that trapdoor falls down and closes off the line, and the gas can't go beyond the shutoff device. Very simple, but they work. They're very effective. They're good. For $500, you can install this in your house, in an apartment house. So you can have something like this. In an apartment house, sometimes you wind up with what to me looks like an absurd situation. This is because these have to be installed on the property owner's side of the meter. If the gas company had installed this before the meter, instead of installing these dozens of these devices, they just would have had to install one. So this is the vagaries of jurisdiction, so to speak. But this technology is really obsolete. And in Japan, following the 1995 Kobe earthquake, the government in Japan mandated that every gas meter in the country of 125 million people be replaced with a new gas meter which had a built-in seismic gas shutoff device built into the meter. This is from Tokyo Gas again. They term these intelligent gas meters. And it's a very simple little electronic card that triggers a spring-loaded device that just closes it off. I visited Tokyo Gas, Osaka Gas, Japan Gas Association, discussed this with them, and so on and so forth. False triggers are not a real problem. Of course, over the years in the entire country, they've had some, but it's not a major problem at all. Trucks going by don't normally trigger these things, not a problem. If they are triggered under non-earthquake conditions, there is that black button in the upper left portion of the meter can just be pressed to reset it, to reopen it. So if you're a homeowner and all of a sudden this thing triggers and you have no gas in the house, you can go out, you can look around, you can smell, see if there's any gas leaks or anything. If not, well, the kids down the street probably were playing baseball and hit the meter with a ball or something. So you just push that button and it reopens the meter and you're back in business. And again, I said, well, you trust the people to do this? And they said, yes, we don't have any problems. People read the instructions. They understand it. So it's just works very well. So we recommend that this be done. And as a matter of fact, the timing in the Lower Mainland is very opportune. The operator, Fortis BC, is in the process of actually applying to replace every gas meter in the Lower Mainland with what they call not intelligent gas meters, but smart meters. Smart meters is the industry terminology for a meter that eliminates the need for a meter reader. It has a little electronic card that communicates through the cell network, and so you don't have to have a human going around every month reading every meter. This simply tells electronically communicates daily how much gas, hourly actually, how much gas you're using. And this was done in California by the Pacific Gas and Electric utility here that serves my house. And I can go online and see how much gas I'm using at the moment. So Fortis is in the Lower Mainland is in the process of planning next year to replace all of their meters with smart meters. And we went to them and said, look, you don't want a smart meter, you want an intelligent meter. You want a meter that not only eliminates, provides more efficiency in terms of reducing your labor costs for meter readers, but you want to include a seismic gas shutoff in the meter. And they've taken that under advisement, and we'll see. We hope to be working with them going forward. So in conclusion, thank you for staying with me. Let me just say, the Lower Mainland is a major economic and cultural center of Canada. It is the highest earthquake risk of any major Canadian city. We looked at 5 different scenario earthquakes. They're going to break water distribution pipes and ignite many fires. Those scenario events, median losses are as much as $10 billion, and can be, in reality, there's uncertainty. It can be somewhat less than that, somewhat more than that. The fire loss is largely insured by you, the Canadian insurers, and will significantly impact you. This risk need not be tolerated and can be significantly reduced. We've made recommendations, developed a portable water supply system, provide secondary water supply for high-rise buildings, that the energy facility seismic vulnerability should be assessed, and the intelligent meters implemented. We've briefed water, fire, and building officials and the energy sector on these findings. Insurance companies are aware of this. The ICLR Insurance Advisory Committee has been briefed, and the report today is going to all of ICLR's member insurers. The insurance industry, I think it's fair to say, enthusiastically supports these recommendations and believes that implementation would significantly reduce the risk of fire damage after a major earthquake. And as with many other loss reduction measures, Canadian insurance industry looks forward to supporting these efforts. So thank you for your time. I hope you've been able to stay with me on this. Again, there's a lot of people contributed to this, and we want to thank all of them. And my co-principal investigator, Keith Porter, Professor Porter, and myself, thank you. And we're available for questions right now and by email.
Thanks so much, Charles. That was fantastic. Very interesting, and again, disconcerting. So everybody, if you have any questions on the presentation, please type them into the Q&A box at the bottom of your screen, and we'll take a look at them. I'm going to start things off. Charles, you talked a little bit about what some other cities and countries are doing. I wonder if you can go into a little bit more depth. You've done some major studies on this and similar issues for LA, San Francisco, Tokyo, other places like that. What are fire departments doing there? What are building officials doing there? What are building owners doing, et cetera? I wonder if you could just shed more light on that for us.
Sure. Well, the fire departments, San Francisco is really the role model. Well, Tokyo and San Francisco are really the role models. San Francisco, if you'll pardon the pun, got burned once. They don't want it to happen again. So 1906, of course, was the largest peacetime urban conflagration in history, only exceeded since then by the Tokyo 1923 earthquake and fire that followed it. That fire, by the way, killed 140,000 people. So San Francisco has, following the 1906 earthquake, it built a high-pressure system like Vancouver's dedicated fire protection system. Actually, it's the other way around. Vancouver modeled its system built in the 1990s after San Francisco's. The San Francisco system is much larger. It's 200 kilometers, 120 miles of underground high-pressure pipe Vancouver is on the order of about 20 miles. That system is 100 years old, and I've been working with the city of San Francisco to improve, extend it, and upgrade it. The city of San Francisco passed a $400 million bond measure in 2010 to improve that system, and we'll be spending more money. So they take it very seriously. They're spending hundreds of millions of dollars to protect hundreds of billions of dollars of property values. As a former fire chief said, San Francisco is built to burn. It's all wood construction, although so is Vancouver. So they take it very seriously. They have a number of hose tenders and other specialized equipment. 3 fire boats. They're going out and buying more hose tenders. And Lloyd's of London, by the way, regularly comes to San Francisco and reviews what's being done there. Actually, I'm the consultant to them on this. Keith Porter and I are. We're taking their underwriters around, showing them all the systems. And so the insurance industry is keeping the fire department honest, so to speak, which is good. Los Angeles doesn't have a dedicated fire protection system. In a study funded by the California Seismic Safety Commission, I looked at that and identified that as a Achilles heel, and recommended, did a conceptual design of it actually. But they do have a lot of other capabilities, but I think they're fairly exposed. Coming back to San Francisco, one of the other things that San Francisco has to back up the high pressure system, they have over 200 cisterns. These are underground water tanks at intersections, each of which holds 300 tons of water. That is about 1 hour supply of water for a fire engine. And so these are a backup to the backup. I mean, San Francisco takes this very seriously. Tokyo does not have a dedicated fire protection system, but is actually interlaced. Much of the city is interlaced with canals, water canals, which are a legacy from their pre-industrial era. So they have a hydro-sub-like capability, an extensive amount of it, and they have 14,000 cisterns within the city of Tokyo. So these are underground water tanks throughout the city. The Tokyo Fire Department is the largest fire department in the world, and very capable and professional. I have worked with them often, and Japan Gas Association. So they have a good capability. And Osaka, similar situation. The other cities, Japan, similar situation. Istanbul, I've analyzed them for fire following earthquake also, and they've gone out and bought and they don't have mostly wood construction either, but they've gone out and bought a lot of specialized hydro-sub type equipment and hose tenders just for the issue of fire following earthquake. So I hope that answers. And again, from the point of view of the jurisdictions, California Building Code requires that secondary water supply. And it's not just in California. That's the California Building Code, but comparable codes in Seattle and other seismic portions of the United States require the same kind of secondary water supply. So I hope that answers your question.
Interesting. By the way, I looked up the bank tower fire that you showed, and that event alone costs $50 million in damage and took the lives of 3 firefighters.
Yes, yeah.
We have another question. Can you please comment on the approximate return period of the event that led to the $10 billion fire following scenario?
Well, a full probabilistic analysis was beyond the scope of this current study. The Cascadia subduction zone last ruptured magnitude 9 in 1700, 220 years ago. It's estimated to have a return period on the order of 300 years, give or take. That's a hot topic in the seismological community right now as to, and so that the actual return period on that is, um, there are various estimates of it. Of course, return period might be interpreted as a regular clock-like cycle, and there is some uncertainty or variation associated with that also. So that's the magnitude 9. So within the next, as I gave the diagram, or I showed the Goldfinger paper, which let me try and go back to it maybe. Let's see. Right here, this is Kulkarni et al. Goldfinger is one of the authors. So that shows that. You can go to that. But that's for the main event, so to speak. But prior to that, we expect a number of magnitude 7 shallow crustal events in the Lower Mainland. So in the decades before the magnitude 9, we would expect several, at least 3 or 4 magnitude 7 events under Vancouver Island and underneath the Lower Mainland to occur. So the return period is actually perhaps the wrong terminology to use, because these occur, it's a return period of a cluster of events. So the hazard, the likelihood of magnitude 7 event in the Lower Mainland is significantly higher than the numbers you're seeing highlighted here. So I hope that answers that person's question.
And does the damage totals given include water and smoke damage?
No, these are property damage only, fire damage. It's burnt area. It's actually, we calculate, it's an engineering analysis. We calculate actually the burnt area, and then convert that to a dollar value. But in most buildings, if you've got under this case, the fires are not going to be fought. So most of the buildings are actually going to be a total fire loss. To the extent they're not, certainly there'll be an enormous amount of smoke damage. And in some cases, there won't be any water damage at all, because the fire department will never get there. These fires will burn themselves out. So I think the water and smoke damage in this case are, they're not explicitly calculated, but I don't think they would change the numbers too much. Let me correct that. Again, to the extent that there are buildings nearby that are not affected by the fire, they might be affected by smoke damage. So insurers are better judge of that than myself. But aside from that, I really think it's just a plus alpha on the main number.
Okay, thank you. Can you comment on the approximate cost of adding a shutoff valve to a gas meter?
Yeah, you can go online right now on Alibaba or Amazon and buy a meter. I don't know what you do with it, but you buy a gas meter just like the one you have in your house, and they're typically about $75, about $100, something like that. The gas companies, when they buy them in bulk, of course, and I don't know their costs, but and actually what they're doing is, when they're replacing the gas meters, they buy a few hundred or a few thousand, go out and replace those, take the ones they took off the house and refurbish them and keep going. So they actually don't have to buy very many new ones. But anyway, gas meter is on the order of, say, $100. The cost of putting in bulk, as was done in Japan, of installing the seismic gas shutoff within the meter is a fraction of that value. The Japanese, when I visited them, quoted numbers to me on the order of $10 per meter. We, in our discussions with the gas utility in Lower Mainland, given inflation and everything else, we quoted, we said, we thought the cost might be in the order of $25 for the actual mechanical changes to the meter. Of course, there's no additional cost from the point of view of labor installation. If you're switching out the meter for a smart meter, or an intelligent meter is no difference whatsoever. So it's really frankly a negligible cost for what you get. I hope that answers that question.
Another question, do you recommend that the DFPS be extended per original plan and or into neighboring municipalities with significant risk?
Well, I'm not sure that it was ever planned to extend it outside the city of Vancouver. If I never heard that, and I was a consultant on that. I was intimately involved in the planning and construction of that project. It's owned and operated by the city of Vancouver, so I never heard that it would go to another jurisdiction. But maybe I'm misinterpreting the question. A reasonable question is, would it be wise or useful to extend the DFPS to other parts of the city of Vancouver? And the answer is yes, sort of, case by case. In other words, you can cost justify the extension of the DFPS to other portions of the city of Vancouver where you have a fairly high building density. And that's a significant portion of the city of Vancouver. Whether communities like Burnaby, Delta, North Vancouver should have a comparable dedicated fire protection system in their central business districts, yes, they might be prudent. But what's probably more useful and cost effective is to have a portable water supply system that can be used anywhere within the city with the large diameter hose, the hose tenders, and the hydro subs, which are again specialized pumping equipment, and that is probably a more cost-effective way. So, in summary, DFPS extended beyond its current lines to some other parts of the city of Vancouver. I would say yes. Specifics are devils in the details. For other cities, possibly, but PWSS, portable water supply system, probably a better way to go, which is why we recommended it.
Right, and you mentioned in the report that such a system can be used for things other than fire following quake. It could also be used to dewater areas after floods. It could be used for wildfire, things of that nature.
Thank you for pointing that out, Glenn. Yes, a portable water supply system is a regular toolkit of things that can be used in other situations.
Another question we have here, if a high-rise building is ignited in a fire, does the model treat it as total damage? Total loss.
Yes. Without the secondary water supply, by and large, yes, we did. We actually treated the fire spread as probabilistic. So we're not modeling the fire spread floor by floor for every high-rise building. We're using a prototype high-rise building, and we treat that probabilistically. But the fire departments are not going to be able to respond to the high-rise buildings except to get people out of the building. This is a dirty little secret of the fire service in Western North America. I've had discussions off the record with many of the fire departments I've mentioned, and the chief officers are quite clear that after an earthquake, they're not going to try and fight fires in high-rise buildings. They're just going to try and get the people out of those buildings because they got many other things to deal with, and they just don't have the resources. And sprinklers are very good at limiting the growth of fires or stopping fires in any building, including high rises, if they have the water. There is some residual water in the branches and mains and risers of sprinkler systems, but it's really inadequate for without a secondary water supply. So, by and large, the losses in most high rises are a full burnout.
So that is actually, you just answered another question we had, and that is there anything you can do if there's no access to water? Anything you can do for high rises if they're a light and there's no water? I guess the answer is really not much.
Get out. Get out. Just evacuate. I mean, yes, not much.
Right.
As a matter of fact, nothing.
Is a different topic. Is it possible that the largest energy companies, perhaps the airports and ports as well, might have capacity to pump water and long hoses? And should these be integrated into a regional strategy?
Well, the airport, Vancouver International Airport. We didn't look at their at that facility at all. Again, specialized kind of facility. But of course, they have their crash trucks. They have a very good capability, and those trash trucks are they have their own water supply. They have foam, which is something I didn't mention at all. Foam is a force multiplier, and it improves the. If you have a little amount of water and use foam with it, you significantly improve the efficiency of the water for fire suppression. And the fire at the airports, they have foam. And we saw this in the 2010 San Bruno gas explosion, which killed 38 people here in the Bay Area in San Francisco. And that was a major gas transmission line explosion. And it was near San Francisco Airport, and San Francisco crash trucks responded to that, and they used foam, and it was very effective. Even though there were a lot of houses that were lost in that explosion. I think 38 people were killed, and I think they lost a couple, 40 or 50 houses. I have a report on that. I'm not sure if the question was asking about whether the Vancouver International Airport can protect itself, and I think
it was could other bodies other than fire departments be part of the regional system? So private corporations, big oil and gas facilities, could there be interoperability where they all work together and to create a regional system?
Well, of course, that's up to the local fire service, the fire community in the Lower Mainland. But I think the short answer is yes, no doubt about it. Every other community I know about, the petroleum refineries, the major factories that have fire brigades, all have excellent communications and work closely with the public fire service. The Vancouver International Airport fire protection, I don't know for a fact, but it's probably provided by the city of Vancouver. But whether it is or not is not important. The fire community typically talks and plays well together. And that includes not just the public fire protection, the public fire agencies, but also the private fire agencies to the extent they exist.
Let's see here, another question. Insurance companies and public officials around the world take action to manage earthquake risks. In your experience, is the fire risk considered adequately, or is the focus often largely on managing the shake?
I think managing the shake. I think this is a blind spot for many underwriters and companies. The modelers, again, there are three major modeling companies. RMS, AIR Worldwide, and CoreLogic. Some people would debate whether there's only two now, but in any event, I was a founder of CoreLogic in a former life quite a while ago, and I don't think that they do the same kind of detailed modeling that ICLR has sponsored here. So I think that it's just not well thought through or considered. There is at least one exception to that, is the FM. The FM Factory Mutual, what used to be the Factory Mutual companies, and I think it's now they have consolidated down to FM Global. That is, anybody in the insurance industry knows that they are a specialized and company with unique technological resources, and for their industrial properties, they have thought about fire following earthquake and done assessments to some degree, to quite a degree. But I think on the routine personal lines and even commercial lines, fire following earthquake is just covered with a load factor.
Right.
And that load factor is, in many cases, not well founded.
Thank you. My own question, you note in the report that even well-prepared fire services can be overwhelmed. How did San Francisco fire fare in 1989, Loma Prieta? Was it overwhelmed? How many fires? Was it overwhelmed? How did they handle that situation?
Okay. By the way, let me just add on to what I just said a moment ago about fire following earthquake, my dim view of how it's handled in the industry. If anybody online here has a different opinion, please email me. I'd love to have a dialogue with you and learn, correct it. Let me go back to our emails here. So again, I'm always eager to learn. So please correct me if I'm wrong. To regard to 1989, I'm glad you asked. I was there. All right, so there was that earthquake was a magnitude 7 earthquake, 100 kilometers away from the city of San Francisco. It resulted in 26 ignitions in the city of San Francisco. Most of those, given the dense nature of San Francisco, San Francisco has a population of, at that time, 700,000 people, and it has 42 fire stations. By comparison, city of Vancouver has a population of about 600,000 and 20 fire stations, 20 fire halls, as they're called in Canada. So San Francisco, because of its history, is highly conscious of fire, has a high density, so that the reports people came running in and informed the San Francisco Fire Department about the fires, and they were able to get there pretty quick. By and large, the hydrants were serviceable, functional, they were able to put the fires out. The one big fire I showed you was the Marina fire. That was in an area of soft ground, like the Fraser River Delta. There, the high pressure system failed, as well as the potable system. That report was never received by dispatch. A fire engine on doing a windshield survey of a service area saw the fire and responded to it, could not get through on the radio to the central alarm. And central alarm finally only found out about the fire by watching the TV. And if you recall, that was during the World Series, and the blimp was there to photograph the World Series, and they then were showing pictures of the fire in the marina, and that's how central alarm found out about the fire. So the fire engine that was there could not contain the fire. A few other engines arrived. They did not have water from the hydrants. But San Francisco has the fireboat and at that time, one fireboat, and the hose tenders. They called for the fireboat. The fire was only 2 blocks from the San Francisco Bay. In other words, 2 blocks from the Pacific Ocean, the largest body of water on Earth. The fireboat pulled up, responded. I got to the fire about the same time as the fireboat. Citizens helped to drag hose from the fireboat to the engines at the fire, and they were then able to put the fire out. So San Francisco, in a modest earthquake, the fire department was, I would say, maxed out or close to maxed out, but handled the situation and protected the city. Actually, when I arrived, the incident commander was Chief Harry Brophy, who I knew, and I'm a structural engineer and trained in structural assessment, and Harry was standing in the middle of the street issuing commands, and I went up to him and I said, "Hi, Chief. How can I help you?" He knows me very well. So how can I help you? And he said, "Go help those guys with search and rescue." And that's what I did. But I talked to him later and he said, we had no wind. I thought we were going to lose the whole marina. I was ready to fall back to a defensible position at Union Street, which is about 10 blocks away. He was ready to write off the whole marina, but they had no wind. They got the fireboat in there and they were able to contain that fire. It was touch and go. So I hope that gives you an idea.
You should write a book.
I did.
I think we're gonna. Oh, you did. Sorry.
I have a book called Fire Following Earthquake, by the way. It's American Society of Civil Engineers technical publication. But keep going.
I think we're going to wrap it up with the one last question here, and I'm not sure if you can answer it, but how did the fire following losses that you modeled compare to the losses from shake, liquefaction, tsunami, and so on?
You mean for if the question refers to the estimates for the Lower Mainland?
Right.
Actually, we haven't seen those yet. The Natural Resources of Canada has been working on those estimates for quite a while, and I don't believe they're completed yet. In any event, we didn't compare them.
Right. So to the person who answered that question, the use of the 6th generation shake model in Canada has changed our understanding of the seismicity. So Natural Resources Canada, Geological Survey of Canada is working very hard to develop new maps for the building code and so on and so forth. So our understanding of the risk in the West is changing, and the risk is actually worse. If you want to look at some slightly older data, you can look at the 2013 AIR study that was done for Insurance Bureau of Canada, and you can find that online. So I think we're going to wrap it up at that point. This was excellent. Thank you so much. I welcome everybody to go to our website, ICLR.org, and look at the report. There's also an executive summary of the report there as well, a 4-pager if you don't want to look at the big monster. Yeah, it was very professionally done. It's excellent. And please pass that along to others. Keep an eye on your inbox for the next Friday Forum flyer. And this session has been recorded. It will be on our YouTube channel probably by Monday. The slide deck will be on our website probably also Monday. Also, coming up January 26th next year, ICLR is going to hold a session where we are going to get all the major earthquake modeling companies together in one place to talk about earthquake models, what's going on, what the advancements are, what the concerns are, and so on and so forth. So keep an eye out for more information on that, and maybe put it in your calendar